Okay, in this podcast we're going to take a look at titration where we either have a weak acid or a weak base being titrated with the strong acid or strong base. We'll never do one where we have both a weak acid and a weak base. They're a little bit more complicated than doing just the strong, and we'll see that. Okay, so let's take a look first at a reaction between let's say acetic acid and sodium hydroxide. What students often struggle with the most is writing the equation for what's happening. What I always like to do is take the strong, and here the hydroxide is what's going to be strong. So you're going to be taking that hydroxide and adding it to an acid. Okay? And we're always going to use the net ionics because this sodium is just a spectator and tends to confuse things. Okay. So if I have my hydroxide with a negative ion, which is a negative ion, and my acid, then we're going to transfer this H plus over, and we're going to end up with the conjugate base and water. Okay? All right. So once we do that, we establish equilibrium. And that equilibrium is a double-headed arrow, right? Because it's not strong going to the right. We end up with this weak base that is in water, and we have another reaction. Now this H plus is coming over here. I form this weak acid plus hydroxide, so I end up with a basic solution. Okay, so it's a little bit more complicated. It's a couple of steps. So I form the weak base, reestablish equilibrium, and I end up as a basic solution at equilibrium. Alright. I got a mess here. Alright, so let's take a look at a different weak acid. We have formic acid here plus hydroxide. And we have a proton being swapped, and I end up with the formate ion and water. Alright, so formic acid is a weak acid. I put some of that into a flask, right? And so my initial pH is just the pH of that weak acid that we can figure out using an ice table, right? Alright, so I add my sodium hydroxide to my burette and I put a drop in. So I add a little bit of the hydroxide and I still have a bunch of that weak acid. Okay, when I do that, I end up with some of the conjugate base of that weak acid. The OH that I just added is consumed. So what I end up with is a weak acid and its conjugate base, and what is that? Well, if you recall, that is definition of a buffer. So that's a buffer. In this whole region here where pH is being change in pH is being resisted is what we call the buffer region of a titration that involves a weak acid or a weak base. Okay. So if we wanted to solve for the pH, we can use the Henderson-Hasselbalch equation. Okay. So let's take a look at what happens once I've reached my equivalence point. I have all of my acid consumed, and I have all of my base consumed. And the only thing I have left is the conjugate base. Okay? So this is a weak base, and I'm going to calculate the pH of a weak base using an ice table. Okay? And that's what I'm going to find, is that point right there at the equivalence point. At the equivalence point, I'm going to have a weak base. The weak base, the formate ion. Okay. And that base is going to have hydroxide in it. Once I start adding a strong base, after the equivalence point, I'm going to have both a strong base and a weak base, but the strong base is going to dominate the pH. Okay. Alright, so let's take a look at a titration where I have a strong acid being titrated, titrating with a weak base. So let's say I have HCl and ammonia. HCl is a strong acid, NH3, ammonia is a weak base. what I have is I have the hydronium ion plus the ammonia. I do a swap of one of the H pluses and I end up with ammonium in water. You can also write it the way I like to, which is you have an H plus coming from your acid, right, coming from your HCl. You start with by looking at what your strong is that you're adding, add it to the NH3, and you end up with ammonium. Okay. Once you form the ammonium, it will undergo its own equilibrium with water. Okay, so before we go any further, let's just take a look at ammonium. So if I'm forming ammonium, I want you to answer the question, is that going to act as an acid or as a base? Take a second and think about it. Okay, well hopefully you said it was an acid. It's got an H plus that it can donate. Okay, and when it does that, donates the H plus, it becomes ammonia, the weak base. Okay. And when it does, the water picks up the proton, and I end up with an acidic solution. Okay, so let's take a look at what we have. So we have weak base ammonia in the flask. So the initial pH is the pH of that ammonia all by itself, which I can figure out using a nice table, right? So let's write our equation. We have ammonia plus H plus, because we're adding HCl, and we're coming up with ammonium. Okay. So I add some HCl to the burette, and I start adding it. And as I do that, I am using up a little bit of the NH3, but I'm adding H, and I'm consuming all of the H plus, but I'm making ammonium. And because I have ammonia and its weak acid, I am in my buffer range. Okay, so until I see that inflection point, I'm in my buffer range. Now, one of the things we didn't mention last time is that at the half equivalence point, this point right here, pH is always going to equal the pKa of the conjugate that's being made. Okay, so let's take a look at why that is. So why at the halfway point I've used up half of my ammonia and I produced an equal amount of, and I've produced half as much or an equal amount of ammonium. Okay? Trying to catch up with myself here. Alright. And that's because if you remember the Henderson-Hasselbalch equation, pH is pKa plus the log of B, the base over the acid. And at this point, I have the same amount of base, the ammonia, as I do the ammonium. So it's the log of 1, which is 0, so pH is going to equal pKa. Always. When you have something that's weak that you're starting with, titrating with something strong, the halfway point, halfway to the equivalence point, is always pH is going to equal pKa. Okay, so at the equivalence point, all we have is ammonium, okay, which is a weak acid, so the pH is going to be less than 7. We can find the pH by looking at what happens when I add it to water, okay? So first of all, let's take a look. If I am adding sodium hydroxide, let's say to formic acid, what is my net ionic base reaction going to be? Take a second and think about that. Okay. So what I always like to do is look at the strong. The strong in this case is the hydroxide, so I look for the hydroxide in the reaction. That's what I start with. If it's a base, it's going to react with an acid, so I need an acid with it, so I need something that has the H on it. So the choice is going to be option 3. Alright, so let's take a look at what happens if I add some sodium hydroxide to this formic acid. The first thing you have to do is write that equation that we just agreed on. Okay, I need to do an ICF. This is a one-way reaction, right? We're going to completion. So I got to figure out, if I'm doing ICF, I need to use moles, right? So I got to figure out how many moles I have, and I know that moles is equal to molarity times liters. So I know I have 0.001 moles of the hydroxide. I have 0.0045 moles of the acetic acid, or the formic acid. I originally have no of the formate ion, right? I'm going to use up whatever's I have less of here, and that's going to be the hydroxide. But I'm going to make some formate ion, okay? So at equilibrium, this is what I have. So this is a buffer, right? I'm still in the buffer region. I'm not at the equivalence point yet. So I can use Henderson-Hasselbalch, okay? So the pH is going to be, and plus I have a weak acid and its conjugate, right? No hydroxide. So I'm going to use Henderson-Hasselbalch. I got to recognize that which is the base and which is the acid, right? All right, I'm given the Ka, which is what I need, and my base is the oops, I think I did this wrong. Yep, I have to reverse those. The base is 0.001 and the acid is 0.0035. And when I do that, I get 3.77 is my pKa. I add the log of the base of the acid, and I get a pH of 3.23. Which makes sense, right? Should make sense. Okay, now we're going to look at the most difficult part of titrations with weak acids or bases and the strong of the opposite, which is to look at what happens when we're at the equivalence point. So in this problem, we're told that we are at the equivalence point, and we have sodium hydroxide being added to formic acid. So the first thing we need to ask ourselves is, should the pH be above or below 7? Because we're adding a strong base to a weak acid, it should be above 7, should be a basic pH. So let's take a look. So the first thing we have to do is write our balance equation. So I've got a strong base, so I'm going to start off with my hydroxide. I've got to add it to an acid. I'm going to use the formic acid. It's going to lose the formic acid will lose an H to the hydroxide, and I'll end up with the formate ion. Okay, once I've done that, I can look at my concentrations, which is the same thing we did in the last calculation. It was 0.0045. And because we're at the equivalence point, the hydroxide concentration is going to be the same as the acid concentration. So I'm going to lose that same amount from both the base and the acid, but I'm going to form that amount for the conjugate base of that acid. So at my equivalence point, what I have is only a weak base in solution. So what I need to do is figure out what the pH is of that weak base. So if you remember, if we have a weak acid or a weak base, we use an ICE table. So I've got to look at what happens with that weak base in solution with water. So the water is going to lose a hydrogen. It's going to be in equilibrium. And I'm going to form the weak acid and hydroxide. And because I have hydroxide, I'm going to have a basic solution. Because this is a weak base in its conjugate, I need to do an ICE table, and I need to use molarity. Okay, so let's do the ICE. If I look at trying to find the molarity of the hydroxide, I know the volume of the sodium hydroxide, but I don't know the volume of the acid. So in order to figure out, I'm sorry, I know the volume of the acid, but I don't know the volume of the sodium hydroxide that I use. But I can figure that out, right? Because what I know is I have 0.045 moles, and I know that the base is 0.1 molar. So what I know is I have 0.045 liters. So I'm going to add the volume of the solution together in order to get the total molarity of that base. So I'm going to put that molarity. The molarity is 0.060, and I'm going to put that in the table. That the molarity of the should be of the weak base. Okay. And I have initially no conjugate. Okay. And no hydroxide. I'm going to lose X, gain X. Okay. Now I'm down to a typical ice table problem. Okay. So now I need a KB because I have a basic solution. I don't have KB. I'm given Ka, so I've got to find my KB. You know how to do that. And that's going to be equal to x squared over 0.06 minus x. I can eliminate x because it should be small because I have a very large KB. So x is going to be 1.96 times 10 to the minus 6th, and that is going to represent my hydroxide concentration, so I can use the negative of the log of that to get the pOH, and once I have that, I can subtract it from 14 to get the pH of 8.27. So we had said it should be larger than 7, and in fact it is, but that's a lot of work. It's 2 steps, and it involves going back and forth between moles and molarity, a lot of stuff to keep straight. So the way you figure out how to do this is to do a lot of practice. Okay, let's take a look at another where I'm trying to calculate the equivalence point for a titration where I have 0.1 molar HCl, now with a different base. Now it's methylamine, didn't give you the formula for it, but it's CH3NH2, or we could just call it base, B for base. Okay, so let's go back. Alright, so if I look at this, I'm adding the strong acid H plus to the base, and I end up with BH plus, right? The conjugate. Alright, I'm using ICF table. It's a one-way reaction. My pH should be below 7 because I'm adding a strong acid to a weak base. Okay. If you notice in this problem, if I'm trying to put moles in here, I'm not given any volume. So I can pick any volume I want. And once I pick a volume, then it will dictate the volume of the other substance. But let's just say we have 10 milliliters of the acid. Alright, so I can multiply the volume times the concentration to get the moles, and it's 0.001. And because I'm at the equivalence point, I'm going to have the same concentration of the base. The conjugate is going to be 0 to start. I'm going to lose 0.001 of each because it's at the equivalence point. I'm going to end up with the weak acid. So that's the only thing I have at equivalence. So I'm going to take that acid and look at what happens to it for pH. So when it goes into water, the H plus is going to come off, and it's going to become the hydronium ion. And I'm going to have the conjugate base. Okay. And now I need to use an ice table. I'm at equilibrium. Right, I got an equilibrium reaction, and I've got to use molarity. So if I look at, I have the concentration or the number of moles of the base, and I'm going to divide it by the total volume. So I know what the volume of the acid was, the HCl was, but I don't know the volume of the base. But I do know that I need 0.001 moles of it, and I do know that it has a molarity of 0.2 moles per liter, so that's going to be 0.005 liters. Okay, if I put that value in here, and I divide moles by liters, I get molarity. So I'm going to start with 0.067. I have no conjugate base to start with, and no H3O+. I'm going to lose X and gain X. So now I have a typical ICE problem. I don't have, I need a Ka. I'm given a Kb. So I need to figure out my Kb. And I'm going to set that equal to x squared, right, over 0.067 minus x. I can eliminate x. When I do that, I end up with x squared is 1.52 times 10 to the minus 12. And x is right here. And if I take the negative of the log of that, I get a pH of 5.91. which is below 7, which is what we predicted. Okay.